than uh, certainly less than 1%. So it's quite small. All right. And now in the next exercise, if we assume that there's actually $1.55 trillion in US currency circulating globally, then all we have to do is to calculate the value of the counterfeit bills is just multiply P of A, that's the relative frequency, times this global total of 1.55 trillion. Now, for me, I found it convenient to write these numbers in scientific notation. So you saw up here in the first solution, I did write this value, 175 over 219, 130, you see it there. And so to get scientific notation, you have a leading factor out here, which is a number between typically 0 and 10, strictly between, okay? So the way we write our scientific notation is align the factor in front so that it's this number between 0 and 10. And then if we have to adjust the power of 10, either by moving the decimal point to the left or to the right. In this case, we have to move that decimal place 1, 2, 3, 4. And then we have a number 7.99, which is a number between 0 and 10. And since we moved it to the right 4 decimal places, our factor of 10 is 10 to the minus 4. Just move 4 places to the right, okay? And what I did here is I wrote $1.55 trillion in scientific notation. Trillions are 10 to the 12th, right? Thousands, 10 to the 3rd. Millions, 10 to the 6th. Billions, 10 to the 9th. And trillions, 10 to the 12th. And so we've got both of these numbers in scientific notation. And we multiply powers of 10. So all we have to do is add up the exponents. And a -4 plus a 12 is a +8. And then we multiply 7.99 times 1.55. And that gives us another number, 12.38475 times 10 to the 8th. And now we can move the decimal place over to the left and then multiply by 10 to the 9th. And 10 to the 9th is billions. So we come out with approximately 1.24 billion in counterfeit currency in the world. Now, here I am using this funny looking equal sign, and what that tilde over the equal sign means is it's just an approximation. Okay. Do any of you have questions for the about this problem? Any questions? Okay. Are we good? All right. In this last problem, we have the following scenario. Nokia supplies mobile phones in lots of 25. Maybe they're shipped in boxes, and the quality control engineer has to inspect these phones, and she's looking for defective phones and finding out why they're defective. Now, from historical studies, the defective rate of this particular phone is about 0.075%, okay? So that's quite a bit less than 1%. So it's a fairly small number of defective items here, as you would imagine. Nokia is a well-respected manufacturer of phones. Their quality control procedures are very good, and so they have very small defective rates in their phones. Now, so what is the probability of an individual phone being defective? Well, it's just the defective rate, okay? So the probability, let's call it P, of a defective phone, here I'm giving you the number in percent. So to convert that to a decimal, we just divide by 100. That means we move the decimal place over 2 places. Okay, insert zeros. And here we have we move the decimal place 2 places to the left. Okay, because to go from percent to decimal, we have to multiply the percent by 100. Okay, so here we've divided by 100 and we get P as 0.0075. Okay, so converting from percent to decimal, divide by 100, and we get this value here. Okay. Okay, now I'm also identifying the number of phones in the lot, which are 25. Okay, and in your reading from chapters 3 and 4, you have run across the binomial distribution. And let me say a word about the binomial distribution. We've already studied the coin tossing experiment where we toss the coin 3 times and we let X be the number of heads in 3 tosses. And in, I believe, worksheet 2, we actually wrote out the relative frequency table for that distribution, for that random variable. And it turns out to be a binomial distribution with parameters n equal to 3 and p is equal to 1/2. That frequency table that we constructed for that experiment of tossing the coin 3 times, the probability of no heads in 3 tosses is 1/8. The probability of 1 or 2 heads in 3 tosses is 3/8. And the probability of 3 heads in 3 tosses is 1/8. Okay, and we did that basically using, we wrote out the 8 outcomes, we counted the number of outcomes that had 0, 1, 2, or 3 heads, and we took the relative frequency. But actually, this distribution can be written out in the following way. N over X, that's the number of combinations that you can derive from n numbers taking X at a time. Okay, remember X ranges between 0 through n. And you multiply the parameter P, okay, which is in our application here, it's the defective rate, and you raise it to the X power, and then you multiply times 1 minus P times n minus X, okay? And if you were to use this formula to calculate our frequency table from exercise 3, I believe it was, in worksheet 2, you would get, for X equal to 1, 2, 3, you would get 1/8, 3/8, 3/8, and 1/8. So this is actually the theoretical distribution called the binomial distribution. So what we're doing is we're going to model this problem as if it were coin tossing. That is, we're going to toss the coin 25 times with a probability of defective item 0.0075. Okay, so that's our binomial model with parameters n equal to 25 and p equal to 0.0075. Okay, so these are our parameter sets, and with that we can calculate the probability of an event. So let's define the event now. Okay, so up here it says, if the engineer wants to carefully analyze a defective mobile phone, what is the probability of her getting at least one defective phone in a lot of 25? So effectively, what we're calculating is at least one would be the probability that X is greater than or equal to 1. Now here, to get the next expression, we look at the complement of this event. X is greater than or equal to 1. The complement would be that X is equal to 0. All right? That is, that there were no defectives. So if the event is at least one defective, then the complement of that event is that there are no defectives. So to get the probability of the complement, I simply subtract probability that X is 0 from 1, right? And now use our formula for the binomial distribution here. And so again, X is 0, N is 25. So here it is, 25 over 0, okay, times P to the X, X is 0, times 1 minus P. Sometimes we call 1 minus P Q. And we raise that to the n minus x power. In this case, it's 25 minus 0. And then if you take this difference, you get 0.9925, raise it to the 25th power. And then what happened to these two factors here? Well, 25 choose 0. Sometimes we read this, this mathematical notation as 25 choose 0. And that key is on your calculators. And the way that n over x is defined, it's n factorial over n minus x factorial times x factorial. So when x is 0, this number, n 25 choose 0, is just 1. So that number became 1. And then if you raise any value, any positive value to the 0th power, you always get 1. Okay. So now going to the calculator, we can calculate 0.9925 raised to the 25th power and then subtract it from 1, and we come out with the probability that x is greater than or equal to 1, and that's equal to 0.019. Okay. All right. And depending upon the protocols and the quality control procedures, this may be deemed too high or too low. So it may be high enough that the engineer can be reasonably sure of getting at least one defective mobile phone that can be used for analysis. All right. Are there any questions about the solution to number 3?
Yes, actually, I have a question. I got confused when you explained the part of 25 over 0. So that's not a division, kind of? It's not a fraction? It's another thing?
No, it's a special notation for the combinatorial numbers, okay? If you remember the coin tossing experiment when n is 3, all right, so the number of coin tosses of length 3 with exactly two heads, okay, we calculated that to be 3 because we wrote all 8 of the outcomes out. And we saw that with x equal to 2, there were actually 3 of those sequences, right? Let me just write them down. Heads, heads, tails, heads, tails, heads, and tails, heads, heads. Okay, so we've sprinkled the 2 heads in the 3 tosses, and we come up with 3 sequences. So another way to think of that is, let's see, let me, okay, let me explain it this way. So if we have 3 blanks, and we're going to fill them up with heads and tails, think of choosing those spaces to put your heads as simply choosing 2 out of 3. So suppose I choose the first 2 blanks to put my heads, and then I put the tails in the last blank, the 3rd blank. Okay, or I can put my heads in the first and the last toss, right? So I can choose tails to be in the middle, or I can choose the heads to come in the 2nd and 3rd places with the tails in the first toss. So what I've done there is I've chosen 2 of the blanks out of the 3, and I come up with exactly 3 such combinations, all right?
Mm-hmm.
So let's go back to the value 3 over 0 over 2, which is this number. And 3 over, let's just write n over x. N over x is defined to be n factorial over n minus x factorial times x factorial. And remember, factorial is just 2 factorial would be 1 times 2. 3 factorial would be 1 times 2 times 3, which is 6. Okay?
Mm-hmm.
So what is 3 over 2? All right, let's calculate that. By definition, it would be 3 factorial over 3 minus 2 factorial times 2 factorial. So what is 3 factorial? That's 6. 3 minus 2 is 1. 1 factorial is 1. And 2 factorial is 2. So I'm dividing 6 over 2. Did you follow all of that?
Mm-hmm. A little bit. It's kind of confusing to imagine that all that in my mind to
I know.
understand
Yeah,
it.
I don't have the whiteboard here, and I'm not sure exactly. Let's see. This is a Word document here. So let me try this. Okay. Let's see if we can try something here. Okay, so I'm going to do Command Enter here. Okay, it's going to give us a new page here. All right, let me. Okay, so I'm going to take this value here. Let's try. Let's see if we can just copy and paste. Okay, so I'm going to copy and paste this down here. This is my ad hoc whiteboard. Okay. All right. So let me write out the definition of this for you. This is in your text, of course. So this is going to be, let's see. Okay, so I'm going to write a fraction here. Okay, and here's our fraction. So this is defined to be n factorial divided by n minus x factorial times x factorial. That's our definition. Okay, so now remember x factorial is equal to 1 times 2, and so on, all the way to x. Okay. Oh dear. We've got two x's there, don't we? Okay, so let's put a space between these. All right. Okay, now, here in our, when our problem is 3, okay, when n is 3, here we've got 3 factorial, and this turns out to be equal to 1 times 2 times 3, and that's equal to 6. Okay. All right, so let's calculate this now for n equal to 3 and x equal to 2. Okay, so let's use this definition, and it's going to be 3 factorial and then 3 minus 2 factorial here, 3 minus 2 factorial, and then here we have a 3. Okay, here we have the 2, x is 2. All right. Okay, now let's calculate that. So that's equal to, as we just said right here, 3 factorial is 6. So up here, let's insert another equation here. Okay, so this is 6. And in the denominator, what do we have in the denominator? So we divide by 3 minus 2. 3 minus 2 is 1. 1 factorial is 1. And 2 factorial is here 2 factorial is 1 times 2, right?
Mm-hmm.
And that gives us 2. So we're going to divide by 2. And that gives us 3. 6 divided by 2 is 3. So the number of combinations of 2 heads in 3 tosses is 3. And remember, whoops, don't go away. Okay, so, and we listed them before. They were H tails, H tails H, and tails HH. So those are the 3 combinations of 2 heads where you toss the coin 3 times. All right. And similarly, so this value here, so go to your text and look at the binomial distribution. Okay, does that clear up your question, Estella?
Yes, it is way more clear now. Mm-hmm.
Okay, so let me do one more problem here. Let's suppose we toss the coin 10 times. So n, so let's put it here. So we'll let n equal to 10. And how many combinations or how many sequences of heads and tails do we get if we toss the coin n times with exactly, let's say, with exactly 5 heads? Okay, All right, so what we've got here is we're filling up 10 blanks. 1, 2, whoops. 1 space, 2 space, 3 space, 4 space, 5, 6, 7, 8, 9, and 10. Let's count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then in each one of these spaces, I'm going to put 5 heads. And the other 5 spaces, I'm going to put tails. All right, so how many results, how many outcomes do we get if we toss the coin 10 times and we're asking for exactly 5 heads and 5 tails? Well, that number is 10 choose 5. So it's this number here. So let's copy and paste this number right here. And instead of a 3, we'll put a 10, right? That's the number of tosses. And then down here, we'll put the number of heads, which is 5, okay? And then again, we use our formula up here. And we get so we get 10 here. And down here, we get 10 minus 5. And here we get 5. Okay, now I want all of you to take a few seconds here and calculate what this value is. Okay, now some of you have the calculator, have the key on your calculator, and my calculator here is a TI-36X Pro. I referenced this calculator in your syllabus, and it has the key. It's called NCR. So NCR is just this value here. Okay, so let me write in. Typically, your calculators. Let's see. NCR. We don't have a. Okay, so so let's go ahead and calculate this number here. Okay, now this is going to be a little tricky, but let me do it on the calculator first and give you the answer. All right. So here we've got. Okay, so I'm going to type in 10. I'm going to hit my NCR button. And I'm going to type in now 5. And that gives us a value of 252. Oh, where did that go? Cursor was way up there. 252. That would be exactly the number of outcomes that have exactly 5 heads